Okay, so as we start to look at entropy, we can now start to do a little bit of math. You knew it was coming. Because our end goal is to be able to look at a reaction and say, is this reaction going to be spontaneous? Is it going to happen the way we have it written under these conditions all by itself? And if not, what can we do to make it happen? And so we got to get to this point where we can start to get some numbers and start to mathematicalize a little bit as to whether or not a reaction will go. So we need a couple of pieces of information. So in a spontaneous process, if a reaction is going to go on its own, the energy of our final state is more dispersed. We've spread out the energy more than what was originally stored in our system. And so for our system, it will always move to a higher state of disorder or to a higher entropy. If we are going to higher entropy, we are more likely to have a spontaneous reaction. Our thermodynamic quantity associated with disorder and energy is called our entropy. We spent a lot of time talking about this. And this comes back around to kind of our second law of thermodynamics. Our second law of thermodynamics says that for a spontaneous process to occur, it has to result in an increase in the entropy of the universe. And that's super important because it's now not just our system. You also have to look at the surroundings to say, did all of these pieces combined get more entropy than what we started with? Well, then our reaction is spontaneous. So sometimes we have reactions that wouldn't make sense. You wouldn't think that they would go all on their own, but they do because they are creating more entropy. We'll look at some examples. It'll make sense. But end of the day, second law of thermodynamics says, in order to be spontaneous, the universe has to gain entropy. Maybe not just a system, but the universe, both systems and surroundings. Cool. So things to think about. How would the entropy of our surroundings change during an exothermic reaction? So we got a reaction, it gives off a bunch of heat. Well, what does that mean for the gas particles immediately around it? It means that they're going to be moving faster and their disorder would increase. And so for an exothermic reaction, you're always going to gain more entropy because you're gaining more entropy around your system. And so that then plays into our kind of idea of spontaneity or whether or not a reaction is spontaneous. How does the entropy of the surroundings change during an endothermic reaction? Okay, so we got our system, it's absorbing heat from its surroundings. As a result, the surroundings have less temperature or heat energy. That means they move slower, therefore they become more orderly. We would say that it has a decrease in entropy during an endothermic process. So spontaneous endothermic process, something that happens on its own, but yet it takes in heat energy. This would be like melting ice, right? We know it's absorbing heat energy is going in from the surroundings, but because of the amount of entropy that the ice particles are gaining, this process still happens spontaneously at temperatures above 0 degrees. More on that to come. Temperature does affect our spontaneity of our reactions. Throwback question here. Why is the heat of formation for an element 0, but S is greater than 0 for an element? If you remember, H is the heat of formation. Well, because the elements already existed, there's no additional energy to be received or gained by the formation of elements. They are kind of our simplest building blocks, right? There's no other additional heat energy to be absorbed or released. But for S is the disorder. And the arrangement of the particles has nothing to do with the heat energy from the bonds. And so keeping those two quantities separate, thinking about what that means for us is going to be important as we start kind of thinking about spontaneity, because we're going to have to consider both of our pieces here, both our heat energy and our entropy of the system. Cool. Which of the following would be considered non-spontaneous? Methane burning in air, teaspoon of sugar dissolving into hot coffee, and a soft-boiled egg returning to a raw form. Cool. So just a little bit of review as we start to think about our different pieces. Let's talk about the third law of thermodynamics. Our third law of thermodynamics says that a perfect crystal, one that is completely symmetrical, perfectly made, has 0 entropy at a temperature of absolute 0. Okay, so here we are. We need some way to be able to start to quantify the entropy. We need a way to assign numbers to how mixed up our systems are. And that comes from the third law of thermodynamics. We said if we had a perfect crystal where everything is super neat and organized at 0 Kelvin, where nothing is moving, then it has zero entropy, excuse me. What that then means then is if anything exists on the planet above 0 Kelvin, it's now going to have an entropy value. And this is true. This value was defined by Ludwig Boltzmann, this guy formula from before, right? And our third law states perfect crystal at 0 Kelvin has zero entropy, or S equals 0. The entropy of an element or compound under any other temperature and pressure is the entropy gained by converting that substance, by taking that material from 0 Kelvin up to whatever our new temperature is. As a result, these are typically going to be a positive value. They're going to be greater than 0 because they're getting more jumbled up. They gain more heat energy. The particles are going to have a greater disorder. Here we got two crystals. We got magnesium oxide and sodium fluoride. And you'll notice there's a difference in their entropy values. Which one has the greater disorder? Well, it's going to be our sodium and fluoride. It actually comes back to this idea of our Coulomb attractions, right? A 2 plus and 2 minus are more rigidly bound to one another because they've got greater charges attracting between them than our sodium and our fluoride. As a result, these kind of shimmy and shake a little bit more than our magnesium 2 plus and 2 minus. Cool. Just think about this number and what it means for us. We can start to quantify it. We have a way to get this number. So the actual mathematical piece for this, the way we actually find this change in the entropy from 0 to whatever our temperature is calculated using the following formula, that the change in the entropy is going to equal the amount of heat energy that our system has gained, the amount of energy it's either absorbed or released, divided by the temperature we have raised our system to. So our change in entropy for a spontaneous process is this formula here, where Q reverse is the heat either gained or lost by our system during the process where we kind of heat it up from absolute 0 to our current temperature, or whatever our temperature is defined to be. Just quick definition piece, a reversible process is one that can be returned to its original state. So we could theoretically cool down the crystal, right? That's a reversible process. An irreversible process, you can't do that because you'd have to take a different pathway to get there. Don't worry about that so much. This is how we actually figured out. We go, okay, well, we've heated up our system from 0. We said 0, perfect crystal, 0 Kelvin. We heated it up to this temperature. Here's how much energy or how much heat energy went into our substance. That energy must have been absorbed somehow. It must have increased the disorder. Here's how we then calculate the amount of disorder it has gained or lost, changing that heat energy over our temperature of our system. So to determine the value of S, we got to measure the energy transferred as heat under reversible conditions as we go from 0 Kelvin to whatever temp we have said. Usually we do standard temperature and pressure, but more on that in here in just a second. So this is how we actually get this number. This is how we find an entropy. And you're all like, yeah, that's great. Why do I care? Well, it's because we need to know what to do with these values to start to look at reactions. So we're building here a little bit. Sorry, I forgot a dot. Because it's necessary to add energy as heat to raise our temperature, all of our substances are going to have positive entropy values at temperatures above 0 Kelvin. And they're all going to be above 0 Kelvin. 0 Kelvin is absolute 0. You can't go colder than absolute 0. So our entropies, they're all going to be positive. Do watch out just a little bit for the units, joules per Kelvin mole. It's in joules. Enthalpy is in kilojoules. So watch out for that. That's the number one mistake, is we don't get our units to match up. But here's a bunch of them. There's tables. So really all that work to say, here's where that number comes from when we say, oh, here is the entropy of graphite. Take graphite from perfect crystal at 0 to our standard conditions. That's that S with the little circle. S naught means standard conditions. Standard conditions would be a molar of our molar entropy here, or S naught, that's a little knot. That's from taking 1 mole of it from 0 to whatever our temp is. Usually our temperature is 25 degrees Celsius. It's kind of our standard temperature. That would be 1 bar of pressure, essentially 1 atmosphere, and at 1 molar if it's a solution. So we say these are standard state conditions. What it would normally be, kind of our universally agreed standard conditions. And we got a whole bunch of these. There's a bunch in the back of Appendix B. These were all found kind of using this formula, figure out how much heat got absorbed to get to a certain temp to let us start to have these numbers. And then we can start to compare them. Because now we can say, okay, if we go from this substance to this substance, well, what change in entropy would we actually see to go from a gas to a liquid or a solid to a gas? We now have numbers that we can start to do some math with. Cool. So for each of the following, choose which member would have a higher entropy. We've seen this a couple different times, just a little bit of review. Then should be able to justify it or explain why. We're not going to get that, but should be able to check it. So which one would have a higher molar entropy? Would it be a mole of SO2 or a mole of SO3? What about a mole of CO2 in its solid form or a mole of CO2 in its gaseous form? What if we had 3 moles of oxygen or 2 moles of ozone? Okay. 3 moles of oxygen gas or 2 moles of ozone? 1 mole of potassium bromide in its solid form or 1 mole of potassium bromide in its aqueous form? Higher, looking for the higher one. Seawater at midwinter at 2 degrees or in midsummer at 23 degrees. 1 mole of carbon tetrafluoride or 1 mole of carbon tetrachloride? Which one would have the greater molar entropy? Cool. We're going to hit this next time. I just want to kind of think about where these numbers are coming from, and then we'll start plugging these in together when we get back together. Make sure you've got these. Make sure you're feeling okay. Please come with questions when I see you again.